Hello students, today I am continuing the lecture of resonant circuits. In last lecture I am in bandwidth derivation, that part I will continue today. Along with that, parallel resonance circuit, frequency versus susceptance curves, practical parallel resonance circuit and few problems I am going to solve today. In last class, I have shown this expression plus or minus R is equal to omega L minus 1 by omega C. So, resistive part of the network, series network is equal to reactive part of the series RLC network. And this can be written as plus R is equal to omega 2L minus 1 by omega 2C. I have called this as equation 3. And minus R I have represented omega 1L minus 1 by omega 1C. This expression is equation number 4. Later I have added these two expressions. I got the result omega naught square is equal to omega 1 omega 2, and this omega naught is equal to square root of omega 1 omega 2. That means this omega naught I can write it as resonant frequency. The resonant frequency is equal to the geometric mean of two half power frequencies, omega 1 and omega 2. Later, subtract equation 3 minus 4. What we get? Subtract equation 3 minus 4, omega 2L minus omega 1L minus 1 plus 1 by C, I will take common. This will become 1 by omega 1 plus 1 by omega 2 is equal to R minus of minus R will become 2R. So, from this L I will take it outside. The expression will be omega 1, omega 2 minus omega 1 plus here 1 by C. The LCM will become omega 1 omega 2. In the numerator again it will become omega 2 minus omega 1 is equal to 2R. Divide this expression by L. So, L and L cancel each other. Omega 2 minus omega 1 plus this will become 1 by LC into bracket omega 2 minus omega 1 divided by omega 1 and omega 2 I will substitute with omega naught square. So, omega naught square. Here this is equal to 2R by L. Later this 1 by LC, we know the expression omega naught is equal to 1 by root LC. If you square this expression, therefore omega naught square will become only 1 by LC. Use this expression, substitute here, we get omega 2 minus omega 1 plus omega naught square into omega 2 minus omega 1 by omega naught square is equal to 2R by L. Omega naught square cancels. Result we are getting 2 into bracket omega 2 minus omega 1 is equal to 2R by L. So 2 will go, and finally omega 2 minus omega 1 is equal to R by L. This omega 2 I will call it as higher cutoff frequency omega H, and omega 1 is lower cutoff frequency omega L. This is equal to R by L. This is the bandwidth expression. If you want to keep in hertz, the bandwidth in hertz, then expression will become FH minus FL is equal to R by 2 pi L. These two expressions belongs to bandwidth. So individual frequencies, two half power frequencies, can also compute like using this formula. FL is equal to FR minus bandwidth by 2, one expression, and higher cutoff can be calculated as FR plus bandwidth by 2. We can use these two expressions while solving the problems. So before going to the parallel resonance, let us review these definitions, some important terms. I already told impedance, it is a property by virtue of which opposes the flow of AC current measured in ohms. So three expressions you can observe here, impedance expressions for RL, RC and RLC circuit. So in RL circuit, it is R plus JXL impedance is equal to R plus JXL. In capacitive circuit, RC circuit, Z is equal to R minus JXC, it is corrected. Z is equal to R plus JXL into bracket XL minus XC in RLC series circuit. In parallel resonance, these three takes an important role. One is conductance, is a reciprocal of resistance. Another one is susceptance, reciprocal of reactance. And lastly, admittance, reciprocal of impedance. Look at this. It is represented in triangle, and always this conductance and susceptance perpendicular to each other. Its resultant will be admittance Y, by making an angle theta, and omega is the frequency, admittance triangle. Coming to the parallel resonance. In my last lecture, series resonance is explained. In the similar way, parallel resonance circuit also produces the frequency, resonating frequency, under some certain conditions. Parallel resonance circuit is also known as rejector circuit, because at resonance the impedance of the circuit is maximum. Then it rejects the current whose frequency is equal to its resonant frequency. So it is quite opposite to the series resonance. That's why it is called as anti-resonance. So impedance in parallel resonance is maximum. Obviously the current will be minimum, because I is equal to V by Z impedance, that is equal to V by R. So if Z is equal to R, obviously R is also maximum. If resistance is maximum, then current will be minimum in parallel resonance circuit. In parallel resonance, the resultant current through the parallel combination is in phase with the supply voltage, and here also the phase difference pi is 0 and power factor will becomes unity. At resonance, large amount of current circulates between L and C. Due to the energy oscillations, then parallel circuit produces current resonance. Here current IL and IC flowing in opposite directions. That we will discuss in next slide. In parallel resonance circuit, energy stores in the form of magnetic field in the inductor and electric field in the capacitor. So, inductor stores magnetic field in the form of magnetic field and capacitor stores in the form of electric field. Both are oscillating between L and C. Both energies will be transferred back and forth between L and C, which results zero current and energy being drawn from the supply. So, in parallel circuit, the total circuit current is the vectorial sum of the currents flowing through resistance, inductance and capacitance respectively. Now, look at the general parallel resonance circuit. This is the supply voltage, AC supply voltage, and resistance R, L and C are connected in parallel to each other, and voltage across resistance, inductance and capacitance is same. In parallel circuit, voltage across each branch is same, but current divides into three parallel paths, that is IR, IL and IC. Current flowing through the resistance is called as IR, current flows through the inductor is IL and current flowing through the capacitor is IC. And individual currents can be calculated like IR equal to supply voltage divided by R, IL equal to supply voltage divided by XL. Inductor will have the inductive reactance. Similarly, current IC is equal to supply voltage divided by capacitive reactance in the capacitor. And look at this LC circuit, tank circuit. It is familiarly called as tank circuit. Here current IL flows through L and IC flows through the C. So, this IL is coming from the inductor which enters into the, that is IC is in this direction and IL is in this direction, clockwise direction, and IC is anti-clockwise direction. Both are opposite each other, and whenever both are opposite each other, they are equal and opposite, and both will cancel each other, and finally here the reactance will become 0, total reactance will become 0, and finally the resistance remains only in the circuit, and here this part will become open, and only supply voltage and resistance will be present in the circuit, and later total current is equal to Vs by R only. Next, admittance expression is Y is equal to 1 by Z. It can be written as square root of conductance square G square plus susceptance square B square. So, conductance G is equal to 1 by R, and this inductor and capacitor will have susceptances. In inductor, inductive susceptance BL, in capacitor, capacitive susceptance BC occurs. That they can express as inductive susceptance is reciprocal of inductive reactance. So, 1 by XL, I have substituted XL formula here, 1 by 2 pi FL. Similarly, capacitive susceptance BC is equal to 1 by XC. Then that reactance, capacitive reactance is substituted with formula, and we are getting 2 pi FC. As I told, IR is equal to supply voltage by resistance, IL equal to supply voltage by inductive reactance, V by 2 pi FL, and similarly IC equal to V by XC, and it is V into 2FC. So, total current is a vectorial sum of IR, IL and IC. At resonance, currents IL and IC are equal and cancelling, giving a net reactive current equal to 0. IL and IC cancel each other and resultant current will become 0. And here you can see total current is equal to square root of IR square plus 0 square, and finally we are getting IR. Total current is equal to current flowing through the resistance only. Then coming to the admittance for that circuit, Y is equal to Z plus BL plus BC. I have substituted conductance with 1 by R, inductive susceptance with 1 by J omega L, it is XL, it is omega L is XL, and BC it is 1 by XC, 1 by 1 over omega C goes to the numerator side. And finally we are getting this expression. Under resonant condition, XL is equal to XC and 2 pi FL is equal to 1 by 2 pi FC. And if you compute this, again we are getting the same expression like series resonance. FR is equal to 1 by 2 pi root LC in terms of Hertz, or omega R is equal to 1 by root LC in radians. So, how LC tank circuit performs? So, here supply voltage, current IR flows through the resistance, and if you put together, if you take LC, and resultant current will be, because both currents are flowing in opposite directions, so resultant will be IL minus IC, and finally both will cancel each other at resonance, and reactive current is 0 here, and reactance will become infinite and it is open, circuit will be open. If reactance is, total reactance is infinite, then circuit will become open. If it is open, then no more current flows through here, and only current, total current is equal to current flowing through the resistance. Look at the graphs, susceptance versus frequency we have taken. So, first graph is frequency versus capacitive susceptance. Here we have taken capacitive frequency versus inductive susceptance. So, here inductive susceptance is inversely proportional to the frequency, you see 1 by F. So, as long as frequency is decreased to 0, and here inductive susceptance will become infinite, and as long as frequency is increased, the inductive susceptance decreases. It is inversely proportional, and the curve is like hyperbolic curve. If you plot the graph, we are getting this nature. Then coming to the second graph, it is capacitive susceptance versus frequency, and relation for that is capacitive susceptance is directly proportional to the frequency. If frequency increases, capacitive susceptance also increases, and it's a, if you plot a graph, it looks like a straight line. So, it is directly proportional and it is linear in nature. And coming to the third graph, both susceptances are taken in this graph versus frequency, and the curve is passing through this axis, that is this axis, and this point is called as resonating frequency, because this curve is intersected the axis, and that point is called as resonating frequency. And here these two arrows indicates that the value of BL and BC, both susceptances it will gives, and whenever both are equal, we are getting the resultant we are getting, and at that point we are getting resonating condition or resonance. Next, current in parallel resonance. So, frequency versus current plot is shown here, and as I told already, the impedance will be maximum in the parallel resonance circuit. If impedance is maximum, that is also equal to resistance, or if resistance is maximum, current obviously minimum, because conductance is less, because conductance is equal to 1 by R. So, as R increases, conductance also decreases. So, you can observe here G is less here. Next, coming to the practical parallel resonance circuit. So, parallel resonance circuit can be expressed in this way also. R, L in series. For this combination, C is connected in parallel. So, we can form one more expression for this. So, here resistance and inductance are in series. For this combination, capacitor in parallel. This is R, L, it will have XL, and C, it is having XC, and it is connected to the supply. Total current IT, and later it will be divided into two parts. And from this I will write ZL and ZC. What is ZL and what is ZC? ZL is the impedance of this branch, and ZC is the impedance of this branch. So, ZL can be written as R plus JXL. In parallel circuit, I want admittance. Admittance YL is equal to 1 by ZL, that is equal to 1 by R plus JXL. If you rationalize this expression, your YL will become R minus JXL divided by R square plus XL square. This is the admittance at this branch. Next, similarly, I will take ZC. It is, there is no resistance in this branch, so resistance is 0 minus XC. So, 0 minus XC, J XC. So, this is equal to, I want YC, this is equal to 1 by ZC. Substitute here, 1 by ZC value is minus JXC. If you send minus J to the numerator and you substitute XC is equal to 1 by omega C here, omega C goes to the numerator side. Finally, YC is equal to plus J omega C only. After getting YL and YC, then you can add these two. Total admittance Y is equal to YL plus YC. This is equal to R minus JXL divided by R square plus XL square plus J omega C. Here, this expression has both real part and imaginary part. I will separate these two. Real part I will separate first. R divided by R square plus XL square here separately, and I will take plus J outside. Omega C I will write this one, and minus XL divided by this one, R square plus XL square. See, in resonance, the reactive part should be 0, is equal to 0. The reactive term omega c minus this XL by R square plus XL square is equal to 0. So, omega c is equal to, if you equate to this 0, this will become XL. That XL I will write it as omega L divided by R square plus, I will substitute XL value omega L again, omega square L square. This omega cancels. Cross multiply, you will get R square C plus omega square L square C is equal to L. I want omega square. So, omega square L square C is equal to L minus R square C. So, I want only omega square because the resonating frequency is this. This is equal to, divide individually, L divided by L square C minus R square C by L square C. So, L cancel, 1L, and C cancel. So, your expression will be omega square is equal to 1 by LC minus R square by L square only. It is omega square. I want omega, that is resonating frequency omega R, is equal to square root of 1 by LC minus R square by L square. This is an expression for resonant frequency for given circuit, that is practical parallel resonance circuit. In the similar way, this, suppose, look at this circuit, suppose one of the resistance is connected here, then this you call it as RL and this I will call it as RC. Apply same method, then this will become RC minus JXC, that is ZC value, and here it is RC minus JXC. Rationalize this, take the total admittance and substitute and rearrange in the expressions and do the simplification here, and you will get this expression. Final expression for this type of circuit is omega R is equal to 1 by root LC, again square root of RL square minus L by C over RC square minus L by C. This is another alternative expression whenever a resistor comes in series with capacitor. Next, let us solve few examples of series resonance and parallel resonance. So, in this problem, first problem, a series resonance network consisting of resistance 30 ohm, capacitor 2 microfarad and inductance 20 millihenry connected across 9 volt supply. Under resonant condition, you calculate resonant frequency FR, current I, total current, and voltage across inductor and capacitor with quality factor and bandwidth of the circuit. See, represent in the form of circuit, RLC are mentioned here, 9 volts are connected across the supply. So, you know this formula, resonant frequency is equal to 1 by 2 pi root LC, substitute L value and C value. If you compute with calculator, you will get 796 hertz of frequency. This is resonating frequency. Current can be calculated with the supply voltage and resistance given. 9 by 30 is equal to 0.3 amperes you are going to get. If you keep in milliamps, 300 milliamps. So, to find the voltage across inductor and capacitor, we should have XL. If you get XL, that is equal to XC in under resonant condition. Same value will be there. So, XL is equal to 2 pi FL. So, if you substitute F and L values, you will get 100 ohm as the inductive reactance, and capacitive reactance also 100 ohm, because XL equal to XC, and VL is equal to I into XL. 300 milliamps into 100, you will get 30 volts of voltage across inductor. Coming to the quality factor. Quality factor can be find by using this formula, inductive reactance by resistance. 100 by 30, you will get 3.33. For this, there is no units. Later, bandwidth can be computed with resonating frequency by value of Q factor. 796 divided by 3.33 will get 238 Hertz of bandwidth. And as I told already, upper and lower cutoff frequencies can be calculated using the formula FL is equal to resonating frequency minus bandwidth by 2. Substitute here and you will get 677 Hertz. And similarly, upper cutoff frequency is FR, resonating frequency, plus bandwidth by 2, only plus, because it is higher than resonating frequency, and you will get 915 Hertz. You take difference of these two, again you will get same 238. You can represent in the waveform, current waveform, maximum current is 300 milliamps. If you make it 300 by root 2, you will get 212 milliamps at minus 3 dB point. And bandwidth represented 238 Hertz, lower cutoff and upper cutoff with resonating frequencies are mentioned here. In second problem, resistance 4 ohm is given, inductance 500 millihenry given, and capacitance is supposed to calculate in this problem, which is the combination is connected across 100 volts, 50 Hertz supply. And here they asked to calculate capacitance as well as voltage across inductor and capacitor. XL we have to find, use 2 pi FL formula, substitute F and L values and you will get 157.1. XC also same, because both are equal. And capacitance C is equal to 1 by 2 pi F XC, because XC is equal to 1 by 2 pi FC. Just re-alter this and you will get, substitute the values of F and XC and you will get 20.3 microfarad of capacitance. And current, total current in the circuit V by R, 100 volts divided by 4 ohm, 25 amps of current you are going to get. And finally, voltage across inductor is equal to I into XL and you will get 3927.5 volts of voltage. Suppose the problem in example 3, resistance is given, inductance is given and capacitance is given, and they are connected in this fashion. R and L are connected in series, and with that combination C will come in parallel. And use that expression, that is FR is equal to 1 by 2 pi root LC root of this formula, one by LC minus R square by L square. Substitute LC values here, what all the given in the problem, and you will get the result 5.03 kilohertz of resonating frequency. This is another type of parallel circuit problem. And references for network analysis, there are so many textbooks written, and foreign authors and Indian based authors. Can use engineering circuit analysis by William Haight and David Irwin, same title, and Fundamental of Electric Circuits by Charles Alexander, and also Network Analysis by Van Valkenburg. So there are many textbooks, and whichever you feel better and you can refer. And in this occasion, I would like to thank my parents, the VTU e-learning center staff, special officer and staff, and management VV Sangha Ballari, Karnataka, and principal of ROMAC Ballari, and also our beloved HOD Dr. S.M. Shashidhar, HOD of EEE ROMAC Ballari. So with this I will conclude my lecture, and these two sessions I have taken as per the VTU syllabus only, but many things are there in resonant circuits that you go through the textbooks and any material, and practical applications or many applications, so that there you have to follow, and applications are variety of applications in electronic circuitry, in tuning circuits, and in filtering also we are using resonating circuits, and as a filter, and radio and TV receiving stations, the resonance will takes an important role, very important role in communication side, in electronics and communication engineering. In communication engineering side, frequency takes an important role, especially resonating frequency. And what we are looking the channels, so variety of so many channels will have different bandwidth and all those things, and in applications you can see. So thank you one and all.